Hello again, my name's Daniel and this is video 3 in how to convert an old organ into a MIDI controller so that you can use virtual instrument softwares such as Hauptwerk to play beautiful music. I'm going to play Jesus Remains My Joy by Johann Sebastian Bach. In this video, I want to talk about how to program the microcontroller to read the inputs of the notes and output the MIDI signal. To do that, we need to also talk about how to debounce the keys and some of the principles surrounding that. If you remember from our last video, we talked about the matrix arrangement of the organ electronics. How does this work? A quick refresher. So we have column 0, column 1, column 2, and column 3, and these are connected to different pins on the microcontroller. And then we have 2 rows. And again, these row 0 is connected to a pin on the microcontroller, and as is row 1 is connected to a pin. Just say that column 0 is set to ground. Now, if we were to press key A and close the switch, current will flow from 5 volts across the resistor, down here, through the closed A switch, through the diode, down to ground. And the voltage will drop across the resistor, causing this point to go from 5 volts down to 0 volts. Now, if you were to write a piece of code in the microcontroller that says, okay, tell me what the state of pin 1 is. If the switch is open, it'll just be 5 volts. But if the switch is closed and this is set to ground, it will then read 0. So then we could set this one back to float and set column 1 to ground. Now, if B is pressed, the same thing will happen. The current will flow out of here, down here, through B, through the diode, down to here, and then you'll get 0 volts here because the voltage drops across the resistor. What about over here? Well, if you press key F, the same thing will happen. Current will flow from 5 volts across the resistor, down here, through F, through the diode, down to ground because column 1 is set to ground. So then if you query pin 2, it'll say, if F is pressed, that it's now at 0 volts because the current will be flowing and the voltage will drop across the resistor. But if F is not pressed, then this will remain at 5 volts because no current will drop across the resistor and this is just connected to nothing. So when it comes to programming the microcontroller, this is the logic that needs to be used. For each of these columns, the first thing we want to do is set a column to ground like I just talked about. So we'll set column 0 to ground. Then for each of these rows, we want to determine if the signal has gone to 0 volts or whether it remains at 5 volts. And depending on the result of that query, we either send a MIDI signal, note on signal, or we send a MIDI signal, note off signal. Start with column 0, then you query this, then you set this back to float, and then you set this to ground. then you query that, then you query that, then you set that back to float, then you set this to ground, query that, then set it back to float. But then you set that to ground and then you query that and query that. And so this is the flow chart of how the logic works. So for each column, set the column to ground, and then for each row, you then check to see if it's gone to 0 or 5 volts. And this involves debouncing, which I'll get into next. All right, what is debouncing of switches? So when switches operate, they don't just close and make contact instantly. They actually bounce. So if you can imagine something massive like a tree branch falling on the ground, it's not just going to go bonk. It'll often like go bonk and bounce. Then that happens over about 1 second as it sort of finds its position on the ground. Well, smaller things do the same thing, they just do it on a much smaller scale. So small switches will go in slow motion, bounce up and down, and then finally settle. But to us, it just looks like they've closed. But the microcontroller can see on such a small time scale that those bounces actually matter a lot and can give you really unpredictable results unless you account for it. So here's a graph of voltage over time. This is 5 volts here. Now, if this is set to ground and you close this switch, the switch won't instantly close, it'll bounce as I've just demonstrated. So what you're going to see on the graph is you're going to see 5 volts steady because the switch hasn't operated yet. But as soon as that switch is pressed, you'll then get this happen. And then it will come down to 0. And there'll be like any number of bounces, and all of this area here is like undefined. It could read 5, it could read 0, it could read 5, could read 0, until it stopped bouncing and it settled down to 0. Now, another thing about this is that the microcontroller doesn't know all of this signal. It only knows the points at which you are querying to see what the state of the inputs is. So you might have a point here, then might have a point down here, point 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 here. And what the algorithm in the microcontroller needs to do is to look for a certain amount of time over which there are consistent results. So consistently low or consistently high. And then only after a certain amount of time, so say 10 milliseconds, only after 10 milliseconds, it will then register that it has changed state. Now in this case, we've gone from 5 volts down to 0 volts. So that's called a falling edge. If it goes from 0 volts up to 5 volts, then that's called a rising edge. So now you can understand this algorithm a little bit more. So for each column and each row, so on an individual row for an individual column, you first want to update the debounce, which means you're adding another one of these points to the graph. And then you go through every other row and every other column, and then you get back to the same row and column, and then you add another point to the graph, which might be this one. Then you go through every other row and every other column, and then you get back to it again, and you add another point. And then over time, you develop these points. And then the algorithm can determine when you've had at least 10 milliseconds or a time of your choosing of points to show that the state has actually changed. So another way to think about this is that every single note on the keyboard has its own graph that is kept track of in the software. So it goes one by one and checks every single note. And every time it checks a note, as it goes through all the rows and the columns, it puts a dot on the graph. So for this note, for example, it'll show 5 volts because it's not being pushed. And then the program will go to this one, it'll be 5 volts. On the graph for this note, it'll be 5 volts. But when it gets to this note, because I've pushed it, and it's connected now to ground, when it gets to the right row on the column, it'll put 0 volts. And then it will go through every other note, adding a point to its graph, get back to this one, and it will put 0 volts again, or whatever it detects. So actually it has to scan through every single other note before it puts another dot on the graph for each individual note. What you have to realize about electronics is that it's incredibly fast. Like, we can't understand or appreciate how fast it can do it. So like, it can scan through every single key in like the smallest amount of time. And so even though it's scanning every single key between each time it puts a dot on the graph, it still has enough time to detect the discrepancies in the bounces. So that's why we have to do this debouncing. Now, in the programming of the microcontroller, I'm using a library called bounce2. So you can read the documentation about how the library works, but I just wanted to show you here these graphs. By default, the bounce library uses the stable interval to process the debouncing. This is simpler to understand and can cancel unwanted noise. So this is the one we want to use. So you get all this, as the switch bounces, you get all this up and down noise, but you need to have this stable interval. So that's what the debouncing algorithm is able to do for us. I use the Teensy 4.1 development board. This one here, I believe, Teensy USB board version 4.1 without Ethernet chip. You can see that all along here it's got a lot of different inputs and outputs. So down here you can see the total I/O pins, 55. So that's quite a high number, so that's a good thing. You also want some analog inputs. So you want as many analog inputs as you have swell pedals. Another good thing about this microcontroller is the high clock speed. So the higher the clock speed, the faster the CPU can execute your code. So this is significantly faster than the Arduinos. I think they're 16 megahertz, whereas this is 600. But to be honest, you'll probably be fine with an Arduino, although I have not tested it myself. Another good thing about the Teensy 4.1 is that it can do USB MIDI, which makes it a lot easier. If you don't have USB MIDI, you have to use serial communication and wire in MIDI connectors into your microcontroller. So why bother with all of that when you can just have USB MIDI? It's very easy and has worked very well for me. I'll now step you through some of my code. So here's the main loop of the program. So this is what the program continuously does over and over again, everything within this loop. So the first thing that we want to do is loop through all the columns, like we said over here in this diagram. For integer column equal to 0 through to the number of columns, then increment the integer by 1 every time the loop runs. So what we want to do is set the pin mode for the particular column which we're talking about. So firstly column 0, then column 1, etc. Set it to output, and then digital write column pin, the same column pin. So the first time the loop runs, it'll be column 0. Set it to low. So this is doing this. Set column to ground. So that's what this code here is. It's setting it to ground. This delay I'll explain later. The next thing we want to do is loop through all the rows, and that is with this for loop. So for integer r equals 0, so starting at 0, up to the number of rows, incrementing the row by 1 each time the loop runs. Okay, so this row here is updating the debounce algorithm. So basically putting a dot on the graph as we talked about, and that's here, update the debounce. Now, if the debounce detects a falling edge, we then want to send a USB MIDI signal. So we'll talk more about this later. If the signal rises here, if debounces for the particular row and column we're talking about rows, then we want to send a USB signal, send note off. And then at the end, we want to set column back to float. So you can see how my actual code very much follows this format here. Now, this here is all for debugging. It's just to send information back to the screen on my computer so I can understand what the algorithm is doing. I could comment it out as I have done in this section. Another handy thing for debugging is using the LED on the Teensy 4.1. So pin 13 is connected to a LED. So when I press a note, it turns the LED on. And when a note is released and you get this debounce rising edge, then I set it to low. So then I can see if these pieces of code are being activated. I'll now take you through some of the setup for the program. So the libraries that you need to use is midi.h, that's for the USB MIDI, and the bounce.2. And this CMath gets used for the swell pedal programming, which we'll talk about in a future video. Here I'm creating some variables. So first of all, I create a variable for the LED pin, which is pin 13. Now the only reason to do this is just for convenience, so you don't have to write 13, you can just write LED pin, which is a bit more intuitive when you're reading your programming. I've created an integer called note velocity 127 because an organ doesn't have velocity sensing like a digital piano. So this is a constant integer for the whole program. Again, a constant integer for the whole program, which is my debounce time, which is that time we talked about on the graph over which you need to have consistent results in order to have a falling or a rising edge. These variables here are for the analog input for the swell controls, so we'll talk about that in a future video. Now here I'm creating the row and column variables. So how many rows do we have? We have 10 rows because each of the two keyboards has 4 different buses or 4 rows. They're those metal rods we saw in a previous video. So that's 8 rows, and then the bass pedals have 2 rows, so that's 10. And then as we've also talked about, the number of columns in this implementation is 16. Now here I'm defining which pins of the microcontroller correspond to the rows we want to keep track of. So I'm saying row 0 is pin 33, row 1 is pin 34, row 2 is pin 35, etc. And same for the columns here. It's just for easy reference later, so I can just, from now on, I can just refer to row pins number 1 in the program. Now this is an important piece of data in the program. This is where we map out which row and column corresponds to which musical note. So in MIDI, every single musical note or pitch is assigned an integer. So you can see a piano keyboard here. So middle C is note 60, C sharp is note 61, D up here is 74, and then the next D is 86. And so we need to define which, for each combination of row and column, so say row 1, column 6, we need to tell it which note is it in MIDI. So for example, in row 9, column 15, it's 50 in this case, or row 5, column 5, note 62. And so this is actually not exactly how my organ is. This is just an example of how it might look. Your implementation you'll have to work out which row and column corresponds to which note. So that is what this matrix here defines. So in my organ, row 0, column 0 is note 36. Now note 36 on an organ is the lowest C. Now MIDI can have multiple channels. So each keyboard should use a different MIDI channel. So for the first 3 rows here, this is for the first keyboard, like the grate, and then this is, say, the swell, and then 2 for the pedals. So that's why I've got channel 1, 2, and 3. So this is essential when you have multiple keyboards. You have to use these channels. I'm defining what channel the MIDI should be sent on. We're using this library bounce2.h. Now this library does a lot of the work for us in terms of the debouncing. So all we have to do is create an array of debounce objects. So every single note on the keyboard, so every single combination of row and columns, has its own debounce object. You can think of these debounce objects as individual graphs for every single key on the organ. So down here is where we do more setup of all these debounce objects. So we loop through every single row and every single column, and we do these two pieces of code for each row and column. So we attach the row pin, so that's an input, and we set it as an input pull-up. So we spoke about that. They have to be pull-up resistors. And then we set the interval time to the debounce time, which is that constant integer up here of 10. And you can experiment with different values. I found that 10 worked for me. So this then goes and sets up all the debounce objects with the settings that are required. Now this here creates a MIDI instance. So this is just a line of code you need to enable MIDI to work. So the void setup loop will only run once at the start of the program. So this serial begin is just to enable serial communication, which is helpful for debugging, which is this here. See, serial write, serial print. This is very helpful for debugging. This is for the expression pedal, so we'll talk about that at another time. This is where we set up the column pins as inputs floating. So at the start of the program, we want all the inputs to be floating, and it's only when we get to this piece of the code that we would set individual columns as outputs, but then set them back to floating at the end. Here we're looping through all the columns and assigning the columns as inputs. So for example, at column 0, col pin 0, which is column pin 0, which is pin 2 on the microcontroller. So that's saying, this is saying pin mode for pin 2 is an input. That's what that's doing. So here we're setting the LED pin as an output. So later on we can write high or low to that LED pin and see the light flash on or off depending on whether a note's hit or not. So I hope you found that video helpful in learning how to convert an old organ to be a MIDI controller. There's a few more things we can probably talk about in a future video. So one of them is the reason for the delay I mentioned earlier in the video between these two lines of code. That's very important for avoiding ghosting notes on the organ, something that I had a lot of troubles with. Some of the other topics we could talk about in a future video is how to physically connect the microcontroller to the wires of the keyboard and the pedal board. We can probably talk a little bit more about how MIDI works, and we also need to talk about the swell pedal because that uses an analog input on the microcontroller. So thank you for joining us, thanks for watching, and see you next time.